maybe I will not spend too much of time on these. So we talked about this front end, backward. So there are these two dominant compilation model. One is a Holman model, which we study, where we have a front end which generates an abstract syntax tree, which generates an optimizer, which abstract syntax tree is fed to an optimizer, which then generates a target independent IR, and then there is a code generator which takes a target independent or machine independent IR and generates a target program. The Davidson-Fraser model, proposed in Topla's paper in 1984, does something different. It has a front end, it produces an AST, and then it has something called expander, and this is where GCC had original ideas, where the AST will directly be linearized into what is called a register transfer language, or RTL, and then the optimizations will be performed on register transfers, and then there will be a recognizer which will identify which of these register transfer, which of the machine instructions represent these machine register transfer language statements, and that's how we get the target program. Of course, this was the original GCC. Modern GCC has changed a lot. Modern GCC essentially is very much like a Holman model here, where from AST we generate gimbal code, and that's the model that is used by LLVM 2. And typical front ends have a parser and a scanner. The relationship between parser and scanner: parser calls a scanner for every token, and it calls a semantic analyzer and generates an abstract syntax tree and symbol table, and it has various other submodules. Typical backends look like this. There is a machine independent optimizer which will do various things, and there is a code generator, and you studied all this in the preceding lecture, so I'll not spend much time on it. And there is a machine dependent optimizer which will do global register allocation, instruction scheduling, people optimization in a loop until the wisdom of the compiler writer. This is a GNU Tool Chain. Let me skip through this because I don't want to really spend too much on the structure of the compiler. The compilers are really very powerful these days. There's LLVM Tool Chain picture. Let me once again skip that. Let me come to modern challenges, which is the main part of this, and I might overflow this talk by 10 minutes, and I hope you will allow me to do that. So this is where the most interesting part is. Okay, so what is the source of new challenges? So what are the modern challenges? So we talked about the challenges faced by John Backus and his team, and let's talk about the challenges that we face today. Okay, so these are the reasons why modern compilers, in spite of being powerful, very powerful, also have to face several challenges. First, the languages have changed significantly. It hasn't remained as simple language like Fortran. Processors have changed significantly. Problem sizes have changed significantly. Expectations from compilers have changed significantly. Analysis techniques and compiler technology itself has changed significantly. So there was this talk, there was this workshop in IIT Kanpur in 2007 where Frances Ellen had come, and she gave a keynote talk, and an important point that she made in the talk was, she said that the worst thing that has happened to computer science is C, because it brought pointers with it. So we have to look at the perspective in which Ellen would have made the statement. Frances Ellen is a leading compiler writer. She was the first woman Turing awardee, and she's done immense work in compiling, particularly for parallelization, for discovering automatic parallelization. And all her work was in the context of Fortran. So there would be numeric computations in which she would do dependence analysis, and her work would allow discovery of parallel code. Now the point is, as soon as C came, C brought pointers with it, and as soon as you have pointers, all that theory goes for a toss. And therefore, Frances Allen lamented that the worst thing to computer science is C because it brought pointers with it. Fortran was very nice, it didn't have pointers in it. So this is one of this gives you an idea of the kind of challenge that modern compiler has to face, which the earlier compilers didn't have to face. Okay, and then processors have changed significantly. We have GPUs, we have mini core processors, we have embedded processors. Problem sizes have changed significantly. Now we routinely talk about programs running in millions of lines of code. GCC source itself is 3 million lines of code. Firefox code runs in several million lines. Linux kernel code runs in several million lines, and we routinely talk about compiling huge programs. Fortran programs that they compiled were comparatively very small. 50 lines would be considered very big at that one point of time. Expectations have changed significantly. Now people want interprocedural analysis, interprocedural optimization. They want validation of programs, verification of programs. They want to talk about reverse engineering. They want to talk about parallelization, discovery of automatic parallelization. So things have changed a lot. And parsing, analysis techniques and compiler technology has changed a lot. We have parsing, we have data flow analysis, we have parallelism discovery, we have heap analysis, we have polyhedral compilation. So many new things in the compiler technology which didn't exist before. And modern compilers span both theory and practice very deeply. And this is one thing that if you have not already realized it, please appreciate it. Okay. Compiler design and implementation translates deep theory into general, efficient, and scalable practice. Writing a compiler is a lesson in software engineering. Okay. It uses principles, techniques from many areas in computer science. It's a great application of software engineering, makes practical application of deep theory and algorithms and rich data structures, and it uses rich features of computer architecture. Okay. So here is just a list of theory and algorithms. I borrowed the slide from Professor Y. and Srikanth of ISC Bangalore. So uses mathematical logic for type inference and checking, lattice theory for static analysis. I will not go over the entire list and everything. I mean, you would have covered many of these in the course. If not, maybe you could look up the slides will be with you. None of this actually existed when Backus and his team wrote the first Fortran compiler. It also uses rich data structures, sparse representations, 4 arrays representation for scanner and parsing tables, uses stacks, lists, and arrays in symbol tables, trees, DAGs, etc., etc. How do we compile? So, for example, let's take compilation for embedded processors. Okay, so you have an application and you have an architecture. Application may have standard features or it may have non-standard features. Architecture may have standard features or it may have non-standard features. What normally we look at, not what normally we study, is a standard application, a conventional application in a conventional language with a conventional compiling technique and a conventional architecture. However, the scene is disrupted when you bring in non-standard application features, language features, compiling techniques, or architecture features. For example, you might have the same thing, but you might compile it a non-standard architecture features. For example, you might want to make use of spatial addressing modes. You may have on-chip addressable memory. I'm sorry, there's a spelling mistake here. You may have on-chip addressable memory, or you may want to use predicated instructions instead of doing explicit checks that exist in the code, the condition checks that exist in the code. Or you might have non-standard compiling techniques which are used to compile to non-standard architectures. For example, SIMD operations, the vectorization, extracting integer instruction level parallelism for VLIW processors, offset assignment, array reference allocation. There are many optimizations that which require non-standard compilation techniques. Or you might have non-standard applications. For example, multiply and accumulate is very common in embedded processor applications, in DSPs. Okay, you might have special kind of loop instructions. Alternatively, you might use non-standard compiling techniques setting arithmetic modes, circular addressing, special loop instructions, etc. So you may have various things in, I mean, exact details are not important. The big picture that you have to take is there could be variations in the applications, there could be variations in the languages, there could be variations in the compiling technology, and there could be variations in the architecture, and all of these pose some kind of a challenge to modern compilers. Let's look at some specific challenges one by one. So modern challenges, design issues is there are many design issues. For example, one of the biggest design issue in modern compilers is the IR interface. This is the most challenging component of a compiler. When you design and implement a compiler, you might do high theory, but accessing the intermediate representation, accessing the gory details of all the information that is required to store the details of the source program, it is very, very intricate. I mean, both GCC and LLVM have very intricate mechanism of storing intermediate representation. When we write LLVM passes, it's very easy for us because we use built-in functions, but the people who wrote those functions provide the library that allowed you to access IR, that the design and implementation of it is a big engineering feat. The other design issue challenge is retargetability. How do we extend the compiler to a new version of the processor? How do we extend it to a new processor? GCC and LLVM both have their own target description languages where you can describe processors, and GCC target description language is very arcane, very difficult to understand, and yet it has been very, very successful. The next modern challenge is improving performance of the program. So how do we scale analysis to large programs without losing precision? How do we do interprocedural analysis? I mean, we have maybe 5,000 procedures in my program. Do I have to analyze each procedure in isolation, or can I see the effect of one procedure call on the other procedure? How do we scale pointer analysis? You'll be surprised to know that there doesn't exist any modern compiler, including the latest GCC and latest LLVM, that provides us precise flow, context, field sensitive points to information for C programs. To this date, we're talking 2021, there doesn't exist any such production compiler, and the reason is very simple. The technology is not scalable. You can do all this precise analysis for 1,000 lines program, maybe 5,000, but your compiler may be used for compiling maybe 2 million lines of code, and your compiler will simply go to sleep. Your processor will go out of memory. You would not be able to compile, and that is the reason why this has not been included in compiler technology. In fact, that has been one of the most important research goals in my group at IIT Bombay. In 2008, 2007, I set a single one-line goal for my research group. We want to do precise flow, flow sensitive, context sensitive, and field sensitive points to analysis for 1 million lines of programs in tens of minutes. It was a quixotic dream that time. Even now, the dream remains unrealized. But my PhD students, one by one, have come up with very interesting solutions to the problems. We have reached about 150K lines, but we still have not reached 1,000K lines, and there are still research in pipeline. And maybe in a few years down the line, we might be able to reach that goal. Whether we reach that goal or not is not very important. The important point is we end up solving interesting problems on the way, interesting serious challenges on the way, and that's the research agenda, main research agenda of my group. The second point is also a part of my research agenda. How do we increase the precision of analysis? One of my PhD students is looking at how to interleave different analyses to benefit from each other. The other PhD student who just concluded, his thesis was how to exclude infeasible paths. Many of these paths are infeasible in the program. Can we perform analysis by excluding these paths? So that was the other PhD problem in my group. But there are many language issues. How to efficiently compile dynamic features such as closures, higher order functions such as eval in JavaScript. How do we efficiently compile for exceptions? Because exceptions create humongously complicated control flow. You have a control flow from every possible statement to the exception handler, in which case your analysis technique simply goes for a toss. It just becomes very imprecise. So how do we even represent a control flow for exceptions in our analysis without unnecessarily over approximating it and making it meaningless? What guarantees to give in the presence of undefined behavior? For example, memory accesses such as array access out of bound. And designing analysis for features supporting parallelism, do all statements, async statement, thread, synchronization, fork, join, lock, unlock, mutex, semaphore. Some of these features enable parallelism in a sequential language, whereas some enforce sequentiality on essentially parallel execution. And how do we design and analyze programs for extracting parallelism? Then there are target machine issues. How to exploit pipelines. We all know about the Spectre bug, and I won't go into the details. How to use multiple execution units. How to use cache hierarchy. How to use parallel processing using shared memory, distributed memory, or message passing. How to use vector operations. How to use VLIW and superscalar instruction issue. How to exploit all these features. The crux of the matter is the following. Hardware is parallel, whereas the conventional software is sequential. Software view of memory model is what is called strong consistency, which says every execution with the same input should give the same result. That's the software view of model. There are parallel languages, but they have not become the mainstream languages. They haven't become very common. Of course, for some GPUs, we have CUDA, etc. But still, most of the languages continue to be sequential. Hardware view of the memory model is very different. It imposes what is called sequential consistency, where results should coincide with some interleaving of threads. That's the point. It doesn't necessarily, there are threads and you don't know whether this will execute before or that will execute before. You might have any interleaving. One will execute, then the second will execute, or the first statement of the one will execute and the second statement of the second will execute, like this. So you might have this interleaving. Okay, this is parallelism at the granularity of instructions in threads. Going forward, memory architectures give weak consistency, where parallelism is at the granularity of pipeline units of the instructions, such as load, store, buffering, and therefore you issue several instructions and instruction reordering is done based on whose execution unit, which execution unit is free, and for which execution unit the data is available. Software view is stable, understandable. Hardware view is disruptive. Let's look at one example of how it is affecting the languages. So let's look at this simple concurrent program. There are two threads. Variables A and B are thread local. Variables X and Y are shared global variables. So first thread, initial values are X equal to 0, Y equal to 0. First thread says A is equal to X, Y is equal to 1. The second thread says B is equal to Y. And if B is true, then X is equal to 1. And with these two threads, they can share values of X and Y. A and B are local. So what is the result of what are the values in A and B at the end of it? That's the question. So sequential, if we talk about sequential consistency, we have the following possibilities. So we might execute first thread completely. A is equal to X, Y is equal to 1, and then we execute the second thread. So because A is equal to X and X is 0 initially, so A is 1. Y is 1, Y is assigned to 1, so B is Y, so B becomes 1. And B is checked, so X is equal to 1. So eventually we get A is equal to 0 because X is equal to 0, and Y is assigned 1, so we get B is equal to 1 in this interleaving. However, if we were to reverse the order of execution of the threads, if we were to say, let's first execute this thread. So we say B equal to Y. So now Y gets 0. And if B is true, then X is equal to 1. So B is 0. So X is not made 1. So when we execute this thread, we assign the initial value of x to a, which is, so we have a equal to 0, and we have y is equal to 1. So we get the result a equal to b equal to 0 in this particular thread. Okay. However, we could interleave thread in some other way as well. For example, we might execute the first statement of this thread and then the first statement of this thread. So b is equal to y, a is equal to x, and then the second statement of this thread and the first statement of this thread. So we might have this interleaving. Here also we get a equal to b equal to 0. Or we might execute first statement of this thread and this thread completely. So b is equal to y and this blue thread, and then the second statement of the pink thread. Or we might execute the first statement of the blue thread and then the pink thread completely, and then the second statement. Or we might interchange first statement of blue, first statement of pink, second statement of blue, second statement of pink. In either case, we get a equal b. In all these cases, there are only two results that are possible. We have either a equal to 0, b equal to 1, or both a equal to b equal to 0. These are the results that are possible. However, and this is where the things become complicated, there are processors which support what is called relaxed memory consistency. What does it mean? We execute the second statement of the first thread. Now the statements within a thread are not necessarily executed sequentially. Relaxed memory consistency allows you to alter the sequence in a thread on the ground that this uses a and x, this uses y and 1, and there is no data dependence between these two statements. So these two statements could be executed in any order. The sequential consistency said that the statements in a thread have to be executed sequentially. But relaxed memory consistency says no need of a sequence. If you don't have any dependency, then you can execute in any order. This is what's called out of order execution on the processors. So we could have y is equal to 1, and then we say b is equal to y. So now we get b is equal to 1. So we get b is true. So therefore we get x is equal to 1. And now we say a is equal to x. So we get x is equal to 1. So we now have both a is equal to 1 and b is equal to 1. Recall that in the previous example, we didn't have this result, a equal to 1 and b is equal to 1. But this relaxed memory consistency allows it. This, in my opinion, is not good, although the hardware companies are pushing it. And they're pushing it, they want to include, they want this semantics to be included in standard C programs. They're pushing it because their processor can do it. But if you observe here, the argument that there is no data dependence between these two statements is strictly not valid. That is because there is a data dependence across the threads. So we are saying that I'm talking about A and B, but yes, you are using y is equal to 1 and b is set to y from here. So there is a dependency across the threads. So how can you execute this? So you have a is equal to x, and then you are checking x equal to 1, and your y is equal to 1, and your b is equal to y. So it could be debated whether we should look at dependency across threads before reordering the statements. However, the processors have a very local view. They can't look at, in fact, we don't even have analysis techniques that could find out dependencies, such dependencies across threads of shared variable. That's one of the challenges. And because we don't have such things, the processor companies are saying that, C semantics should allow this. Now, when we allow such complicated semantics, obviously understanding the behavior of the program is going to become much, much more difficult. But because processors can execute this, they say that this is one of the optimizations and this might help you. This is an example of architecture feature influencing programming language. What else did John Backus and his team did? They also saw the architecture feature, the design language to support a certain architecture. Language design was not the main goal. Here also, ease of understanding the program is not the main goal. Just because you can execute it, just because there is architecture, therefore it must be executed. That is the philosophy. The clarity of the program, the cleanliness of understanding the program is not very important for these companies. They're saying this should be allowed, which means that your program now becomes much more complex. Your understanding of writing programs now becomes much more complex. So this is a challenge that the modern compilers face. I mean, how would a compiler generate code for this? How would compilers exploit this? And then the people will say, you have a compiler that really doesn't exploit the architecture features, and I can write an assembly program which is faster than the assembly program generated by your compiler. The other set of modern challenges that compilers face is in providing guarantees. How do we guarantee correctness of optimizations? This is hard even for machine independent optimization. It would be much harder for machine dependent optimization. I mean, for example, let's take this particular example. What does it mean to say the execution is correct? If you say everything is possible, then everything is correct by default. But does it correspond to the thing that a programmer had in mind? So if a programmer has certain result in mind, how can we guarantee that a compiler preserves the semantics of that? So verification of a production optimizing compiler is a pipe dream, and I have a couple of slides on this. It requires proving the correctness of translation of all programs. There's something called compiler validation, which is more realistic and yet not been achieved fully. It allows proving the correctness of translation of a given program. So we don't say this compiler will work correctly on all programs, but you're saying, give me a program and I'll show you whether your program has been compiled correctly on this, has been correctly or not. And we can hopefully automate the technique and repeat this for every possible program, thereby achieving the effect similar to compiler verification. The other problem that compilers face is interference with security. Security is becoming a very, very important problem now, particularly considering the fact that modern computation happens on the cloud. So when you are executing something, you are executing in a memory, and the next set of addresses from that memory may be assigned to some other processor, to some other user sitting somewhere in Philadelphia. You are sharing the same memory. How do we know that your memory is not being read by that user's memory? John Backus didn't have to worry about it because his computer was confined to a particular room. But now that is not the case. Computers have crossed frontiers of different countries, and now we don't know which two programs are sharing the memory. We are running this Google Meet here. We are using a certain memory on the same processor. Perhaps somebody sitting in Cambodia is using Google Meet and sharing the same memory. And how do we provide security guarantee? Now, the trouble with this is the following, that what compilers do and what security requires are conflicting. Optimizations disrupt memory view. Correctness of compilation is defined in terms of useful states. Okay. So clearing stack location by writing all zeros. So let's say I don't want to read my memory. After I have finished execution, the data will still remain in the memory. So I want to clear out all the memory. So at the end of my program, I write 0 to all locations in the memory. This is important for security. But as far as compiler optimization is concerned, there is no use of this assignment. Live variables assignment will say, you have said a equal to 0, but there is no use of a, and therefore I'm deleting it. Compiler optimization will simply eliminate these, whereas these statements are required for security. So how do we strike a balance between compiler optimization and security? They have conflicting requirements. Compiler optimization has a way of saying that these computations are redundant, whereas they are redundant within the program, but they are not redundant in the environment in which the program is executing. because of the security considerations. The other problem is optimizations also disrupt timing estimates. So some people carefully write a loop assuming it will take so many milliseconds, and now your optimizer comes and does away with it, and that could spell doom on real-time programs if timing requirements are very important. So these are the other challenges that compilers face. How do we ensure that we do not trouble the user by our technology? Let's talk about compiler verification. So what does compiler verification mean? So you have a program P, and let comp P represent compilation of P, and let S mean P represent the semantics or the meaning of the source of P, and let T mean represent the meaning of the target language. So you have a semantics, you have a meaning of the program P, and you have a compiled program, and you have a meaning of the compiled program on the target machine. This is the source language, this is the target language. So these are two semantics expressed in two different languages. So assume that from the target language we are able to abstract out the meaning. So are we getting to this S mean and abstraction of T mean of comp P? Do they coincide? If they coincide for every program, then we have verified the compiler. We have said that the compiler corrects, our compiler compiles code correctly for every possible program. But this is very, very hard. This is very, very hard. Let's take a simple example of what I mean here. So let's say our source statements are y is equal to 5, x is equal to y plus 1. That's our program. And let's say compilation is on a stack machine, a Java bytecode like thing. So we push 5, and then we store it in A0, and then we push A0, and then we push 1, and then I forgot an add instruction here. There should be an add instruction. We push 1 and then store at A1. So the meaning of this is A0 has 5 and A1 has value 6, and there is a certain stack configuration. Now we can abstract it out saying A0 represents Y and A1 represents X. So this meaning, so these two meanings actually coincide, and we can say that this is indeed correct. But the question is, how do we do it for every possible program without even seeing the program? So we have to repeat this for every source program for P, and therefore it is very hard. It requires reasoning about actual compiler implementation, requires reasoning about the behavior of the compiler for an infinite number of programs and their translations. And its automation seems very, very unlikely. And can we reuse the proof strategy? So we don't know that. Instead, there is something called translation validation, where we repeat the same thing except that we talk about a given program. We don't give guarantee for every program. We say for this particular program, this translation is correct. If you give me some other program, I don't really guarantee that the translation will be correct. And we have a hope of automating it. This is less complex because it involves reasoning about a given pair of source and target programs, and compiler can be made to provide information for verification, and automation seems very likely. This is one of the important research projects at IIT Bombay. My colleagues, Professor Amitabh Sanyal and Professor Supratik Chakravarti, are spearheading this, and they have made interesting progress on this research project. But you can imagine that is a very, very important problem. And then there are challenges of new expectations. For example, new application domains bring in new challenges. So what are the underlying abstractions of the domains that should become first-class citizens in a programming language? There's an effort to design a language and compiler for machine learning algorithms. So what kind of things do machine learning algorithms require? For example, for graphics processing, many people think convolution is a basic computation unit. So can we have convolution operation as a part of our programming language itself, instead of being expressed as a collection of loops and some assignments and multiplications, etc., etc.? Okay. So can we, so there's also an effort to design languages and compilers for streaming applications. I mean, what we do on the internet, we just stream the thing. So we have a stream of data coming in. So there are different kind of uh, uh, operations that are required to be performed. So would the same language that we use, would they be useful there, or do we need to design different languages and different kind of compilers? So that's one frontier. And second frontier, which is very common these days, and I think that's one of the questions that was asked to me on the in my first lecture: can machine learning algorithms help compiler create new optimizations? Can human ingenuity in design of novel algorithms be replaced by machine learning? That's one of the things. And then, can compilers learn from the programs they have compiled and become better over time? Right now, compilers don't do that. There is something called feedback, the profile guided optimization, or feedback driven optimization, FDO, and compilers tend to become better, but they're still not becoming better in the sense anticipated by machine learning. But this is another domain where a lot of people are working. Doesn't seem to be a reality as of now. Some people have used machine learning algorithms for discovering parallelism. So you basically see the kind of patterns and see which are the acceptable patterns. So there's a training set, and then you try and optimize. For the optimization, maybe you can use machine learning, because you can't guarantee that you can optimize every program. So if you're able to optimize 80% of the programs better, that would also be a good win-win.